Hi, in this video, I want to talk a little bit about Noether's theorem, where we're now going to think about it in a field theory setting. We've already seen it in the sort of normal analytical mechanics type setting. How are we going to think about Noether's theorem if we're thinking about field theory? So the first thing I just want to remind you, right, in analytic mechanics, we learned that we have this Lagrangian, which defines our system, and it's a function generally of our spatial coordinates. You can also have Lagrangians that are functions of time, but most of the time when we have our conservative systems, there it's just a function of our space-time, our spatial coordinates, excuse me. And then if we apply the Euler-Lagrange equations, we're taking derivatives of this with respect to our coordinates. So I say x, y, and z. I guess more generally, we often write this as functions of q, which are our generalized coordinates. Which again can be our x, y, and z Cartesian coordinates, or they can be polar coordinates, or again, some other, whatever coordinates you like. So in field theory, now our Lagrangian, which again, we think about our Lagrangian density actually, is now a function of some fields. Phi sub n maybe. So these are some fields. And here I'm just thinking about scalar fields, but again, ultimately we can think about more complicated types of fields, but for now we'll just think of scalar fields. And the fields then are functions of our space-time coordinates. So t, x, y, and z. So our Lagrangian, the thing that it's directly a function of is our fields, and then the fields are functions of the space-time coordinates. Whereas this is different from an analytic mechanics, right? Our Lagrangian was a function of our coordinates. And again, Euler-Lagrange has you varying Lagrangian with respect to the coordinates, and I guess their derivatives. In field theory, our Euler-Lagrange equations have us varying Lagrangian density with respect to the fields phi sub n. All right, so I just want to start by reminding you of that sort of distinction. So with that in the back of our mind, so we want to consider a field theory with fields phi sub n, where n is, right, it's some index. So maybe we have many fields. I don't know how many fields we have. Some set of fields. We want to vary these. I'm going to do some transformation and ask, is that going to be a symmetry transformation for our system or not? So again, with our just analytic mechanics, when our Lagrangian was a function of coordinates, what we considered was some coordinate transformation. Maybe we did some translation or some rotation. Now our transformation that we're going to consider is a transformation of our fields. So we can consider a field transformation where we have our phi's now are phi primes, which is some function or set of functions of our original fields and some small parameter. Right? So again, the phi prime is not, it's not a derivative or anything. It's just telling us it's some different fields. So just like before in analytic mechanics, the transformations we were considering were transformations of our coordinates. Now we're actually considering transforming our fields. And then we're going to ask if this is a symmetry of our Lagrangian. And the statement is that this transformation is a symmetry if the derivative of our Lagrangian with respect to our small parameter is equal to 0, which is to say, if we replace all of our phi's with phi primes, and then in our Lagrangian, and then take the derivative of that Lagrangian with respect to this epsilon, which again, we should think of this as some parameter telling us how big our transformation is. If that derivative is equal to 0, then this is a symmetry, right? This is a symmetry of our system if this is true. From that fact, you can derive, and I'm not going to do it, but you can derive by exploiting the Euler-Lagrange equations, the fact that this object, which I'll call J mu, which is a current, this is equal to the sum over our fields of the derivative of our Lagrangian with respect to the derivatives of the fields times the derivative of our new fields, phi prime, with respect to epsilon. You take that derivative and then you set epsilon equal to 0 in that term. And then, so this sort of looks similar to Noether's theorem, our conserved charges from Noether's theorem in analytic mechanics. Here we're going to end up, if you go through that derivation, you see we end up with this additional term, so minus the Lagrangian, times the derivative of our coordinates with respect to that variation. And this really comes from thinking about the chain rule in this derivation here. Because remember, the fields are functions of our coordinates. So depending on what kind of transformation you have, we might have this additional term here. Okay, so this thing, we can derive that this is a conserved current. Again, if this variation of our Lagrangian with respect to the transformation parameter epsilon, if that goes to 0, and if there's some additional requirement, which is a little bit of a technical detail, we also need this thing to be 0. Although that thing is going to be 0 in most cases of interest. And so, but it is important to also note that that thing also needs to be 0 in order for J to be a conserved current. And again, the statement of J being conserved is that d mu J mu equals 0. So this is what it means for J to be conserved. Okay, so what this means is that you could consider some field transformation where you change your fields in some way. You can take that these new fields, plug them into your Lagrangian, and then check to see if that Lagrangian is indeed symmetric under that transformation. So you just take the derivative with respect to epsilon, see if you get 0. If you don't, then it's not a symmetry of your Lagrangian. If you do, then you say, aha, this is a symmetry of my Lagrangian. And now I can calculate some J mu, which is a conserved current associated with that particular symmetry. Again, with this sidebar that this thing also needs to be true in order for J mu to be our conserved current, which again in this class will generally be the case. And what that means, the statement of conservation is that d mu J mu is equal to 0. And this is a powerful tool. Again, you should always think of symmetries as being things that you can mathematically exploit just to make the math easier. And then more importantly, now that means that we have these conservation principles. And then that's a tool that you can use when solving for various things about your system. Okay, that's a little bit about how Noether's theorem works in the case of field theory. Thanks.